So after the commercial break, we'll talk about the last part of the solution process. This is part 2. This will be video be in 2 parts. So the effects of pressure on solubility. Changes in pressure have very little effect on the solubilities of liquids or solids in liquid solvents. However, increases in pressure increase gas solubilities in liquids. An equilibrium is established between a gas above a liquid solvent and the gas dissolved in a liquid. So this is why we see how this is a forward and reverse arrow here. It's the same size, right? Equilibrium. So now, increasing the pressure of the solute gas above the solution causes gas particles to collide with the liquid surface more often. This causes more gas particles to dissolve in the liquid, right? So an increase in the gas, you're going to be going, it's going to favor the product side. Decrease in the pressure of the gas, it's going to be more effect on the solution side. And we'll talk about this later on. This is Le Chatelier's principle. You don't have to know that name, though, right now. Okay, so carbonated beverages are a good example. So these drinks contain large amounts of carbon dioxide, CO2, dissolved in water. Dissolved CO2 makes the liquid fizz and tingle in your mouth. So, examples, right? Soda, things like that. Seltzer water. And the drinks are bottled under a high pressure of CO2, which forces large amounts of the gas into solution. When the container is opened, the partial pressure of CO2 above the liquid decreases. Immediately, bubbles of CO2 form in the liquid and escape from the bottle. So this can be solved in a formula. Right? So how is the partial pressure of carbon dioxide gas related to the solubility of CO2 in a carbonated beverage? And you can write the relationship in the form of an equation. It's called Henry's Law. So Henry's Law, it's S1 over P1 equals S2 over P2, where S1 is your solubility, where S's are your solubilities, and P's are your pressures. We didn't really talk about gases yet. We're going to talk about this a little later, but some base things here. The units for S1 and S2 are grams per liter. Always. Grams per liter. Now, P1 and P2 are going to be in a pressure unit. And I'm going to give you the 3 they're going to be in. And I'm not going to use any other ones. And I'll make sure the same. If we did gas laws already, I would change them and make you convert things, but I'm not going to do that. So they're all going to be in these 3 units: ATMs, kPAs, and we'll say torr. Right? So both of your units or numbers will be in one of these 3 units, and they're all pressure units. So we'll do an example here. So, if the solubility of a gas, well, first off, I'll write the equation so we can plug these numbers right in. So S1 over P1. Okay, so the solubility of a gas in water is, so first solubility, 0.771, all over 3.5 ATMs. What is the solubility? So X, all over 1 ATM of pressure. So we just have a proportion here. So 0.77 times 1 will be 0.77 equals 3.5x. How do we get x by itself? We know divide. So divide by 3.5. 0.77 divided by 3.5, and we get 0.22 grams per liter. And once again, that's as hard as these get as well. So to finish off part 2 of the solution process. Last slide. Effects of temperature on solubility. So increasing the temperature usually decreases solubility. So as temperature increases, the average kinetic energy of molecules increases. So a greater number of solute molecules are therefore able to escape from the attraction of solvent molecules and return to the gas phase. At higher temperatures, therefore, equilibrium is reached with fewer gas molecules in solution. And gases are generally less soluble. Increasing the temperature usually increases the solubility of solids in liquid, as mentioned previously. The effect of temperature on solubility for a given solute is difficult to predict, and the solubilities of some solutes vary greatly over different temperatures, and those for other solutes hardly change at all. A few solid solutes are actually less soluble at high temperatures. And this concludes our look at the solution process. Have a good day.